Hello. So today we are going to be discussing frequency distributions and summarizing data in tables and graphs. So I was talking last week, or not last week, last lecture, that we have different types of research methods that we follow in statistics, the experimental, correlational, and quasi-experimental. And on top of that, we have two different types of statistics in terms of what we're dealing with, which are descriptive and inferential. So today, when we're covering summarizing data in tables and graphs using frequency distributions, that is referring to descriptive statistics. So without further ado, let's get cracking on summarizing this stuff. So here we are. Again, you have this PowerPoint available to you in Canvas, so you guys can follow along if you're not already. But this is not a group collaboration, I guess, though, if you're talking to, your roommates or what have you. But what I want you guys to do here is convert the decimals into fractions and the decimals into percentages and the percentages into decimals. Why do I ask you guys to do this? Well, we're going to be doing that a lot in statistics, and it's important to understand kind of the difference between them and to clear up any confusion or misunderstanding you have off the bat. If doing this activity you still find yourself having a little trouble, don't hesitate to contact me either through Canvas or email, or come to my office hours and I'll be happy to help you with anything you're struggling with. But I'll give you guys some time. You can pause the video because I'm just going to go straight into explain or just switching each of them over. So pause the video to give yourself a chance to make these conversions, and then I will be right there. So that's where you could have paused it. That would have been the face. But anyway, so I'm just going to start doing this now. So this first one, 0.05, that would be converted to 5%. I'm just going to go down the decimal column here. So 0.25 is 25%. 1.0 is 100%. 0.215 is 21.5%, or that can be rounded to 22%. And this last one here of 0.10 would be 10%. Now flipping over to the percentages portion, we're going to be switching these into decimals. So 7.5% would be 0.075, 42% would be 0.42, 13% 0.13, 36% 0.36, and 89% would be converted as 0.89. Again, if you had any problems or struggled with that in any way, just let me know and I'll be happy to help you with that. But like I said, this isn't just to torture you guys or to bring you back to the olden days of whenever we first learned how to do this, elementary school maybe? I don't know. But we will be doing a lot of this in class for different assignments that we have, for different tests that we use. So it's better to just kind of brush up if it's been a while. Anyway, so let's get started on why the hell do we summarize data? Well, it's easier to process by summarizing large amounts of data. As I mentioned in last lecture, when we have a lot of cases or just a lot of individual scores that we're having to examine, to compare with, it's easier to summarize it quickly as opposed to going through each and every single individual score and dictate things from that. It's a quick summary of observations. So means and standard deviations are going to be the most common descriptive statistics we use. And as I also mentioned in last lecture, it makes inferential statistics that much easier. We do require the use of means and standard deviations in inferential statistics when we calculate certain tests. So just getting the means out of the way just off the bat is a good way to start. So just to kind of show you guys that difference of, oh, well, why should we summarize data? If people think that psychology looks like sitting on a couch and asking people what their feelings are, maybe that's part of it, a certain aspect of it. But in terms of the psychology that I work with, or that you guys are learning right now in this statistics course, your psychology is going to look like this, where it's just an Excel sheet or SPSS. If you move forward and use SPSS or any other statistical tool, it's going to look like a mess. So we use descriptive statistics of average and standard deviation to make the picture on the left not look so atrocious, and it's more manageable. So instead of looking at it and thinking, okay, what am I working with here? We know that this The descriptive statistics table on the right is showing, okay, there's the average score, the average age of men is 30.78, the average humor score is 3.63, and N refers to the number, the sample size. So there are 9 men in this. And then women, 34.44 is their average age, 3.26 is their average humor score, and then there's 32 women that are involved in this. So descriptive statistics using tables and just ways to visualize data is a lot faster, a lot easier to work with, as opposed to looking at this and being overwhelmed by all the possibilities. So anywho, so this video is about frequency distribution. So now we're going to actually discuss what the hell frequency distributions are. So they summarize how often or frequently scores occur in a data set. So if I'm going to ask, you know, one example of a frequency score would be to say, okay, how many, I don't know, how many times do you drink water in a day? So every time, oh, I don't have a water bottle over here. Or how many times do you check your phone in a day? So you pick it up, 1, you know, I can make a tally. That's 1. Okay, that's 2, 3, 4, 5, 6, 7, 8. I don't know, but each frequency is just referring to how often something is done. So if I'm just taking a tally of how many times you check your phone in a day, that would be a frequency score of, oh, you checked your phone 71 times in a given day, or what have you. So these frequency scores can be used for, frequency distributions can be used for grouped data and ungrouped data. So we're going to discuss grouped data first, where we graph it using histograms, and ungrouped data is graphed using traditional bar graphs. They both look similar, histograms and bar graphs. However, there are some minor distinctions that I'll be sure to go over so you guys don't get confused moving forward. But with group data, you create intervals. So if you're going to, let's say, take an 8, have age as a frequency distribution, and you're asking people in, I don't know, maybe all of Fresno State, you have a frequency distribution of age. Maybe the youngest student at Fresno State is going to be, I don't know, 16, 17, depending. I'm not entirely sure, but let's stick with 17, because these smart kids are baffling my mind right now. But we'll stick with 17 as the youngest, and I don't know, maybe the oldest is 82. I don't know, whatever. So to create a frequency distribution using grouped data, the way we would do that for age, for example, would be to group them into age categories. So everyone's 17 to 22. We are going to count all the 17 to 22-year-olds that attend Fresno State, and that's going to be the frequency of the group of 17 to 22. Then we'll do 23 to, you know, etc., and we'll just keep going forward with that until all of the age groups are accommodated for. Everyone from 17 at the youngest to 82 at the oldest. We want to make sure for frequency distributions, we count every single person and not just, oh, we'll start at 17 and then we'll stop at 50. And those older students that are coming back for their education, no, they don't count. No, that's not what you do for frequency distributions. You want to count every single person. So I digress. So that is a grouped data, that is grouped data when we talk about frequency distributions, creating these intervals of groups. So 17 to 22, 23 to 24, or well, that's not the same size, but 23 to 17, 18, 19, 21, 22, 17, 18, 19, 20, 21, 22. So we have a 6 size interval width. So 22, 23, 24, 25, 26, 27, 28. So our next group would be 23 to 28. And then we'll continue on and just count how many we have in that group. But with group data, again, we have these intervals of sets that people fit into. You're either in the 17 to 22-year-old group or you're not. Ungrouped data is where we have sets of scores, or just categories, if you will, distributed within these groups that are already kind of created. So we're not having to look at the data and then create intervals of, oh, 17 to 22-year-olds, but you can think of ungrouped data as, oh, they're already in categories. So maybe we're looking, instead of looking at ages at Fresno State and how many people fall within the intervals of age, we're counting how many people are in each major. So we have business, and that's a broad category because I know there's a lot of different aspects to business, but we have, let's stick with the College of Science and Math. We have physics, we have chemistry, we have psychology, we have biology. We have all these different groups that are predetermined. We have majors that exist on our campus, and we just count how many people are in each, the frequency of scores within each major. So that just translates to how many students, and then boom. So a simple frequency distribution, again, this is used for both group data and ungrouped data. And it's essentially just a table that shows how many people are in either each interval for group data or in each category for ungrouped data. So how many 17 to 22-year-olds do we have? And then, you know, 2,500 or whatever. And then how many 23 to 28-year-olds we have? Oh, 2,600, whatever. Or with group data, how many biology majors do we have? How many chemistry majors do we have? So the simple frequency distribution is a table that just shows your intervals or your categories or your majors in that particular example. And then the number of people or individuals or scores or data points or what have you that fit into that group. That's what that is. So to make a simple frequency distribution, you have to do three things. First, you have to find the real range, which is different than the range slightly, but there's still a difference. You have to find the interval width, and then you have to construct the frequency distribution itself. So I have some data here that is taken from the book, and this is showing, I believe it's showing like the number of minutes that children spend watching television in a day. So what we do to find the real range, which again is the first thing we have to do to create a simple frequency distribution, is to take the largest number in the data set, subtracted by the smallest number, and then add 1. So here we have, I've circled it for you to make it a lot easier in red, but we have 175 is the largest number in this data set, and 0 is the smallest number. So we take 175 minus 0, which is 175, and then we add 1, so our real range of this data set is 176. Okay, cool, bitchin', neat, moving forward. That was simple. Now we find the interval width. So to do that, we take we divide the real range by the number of intervals that we want. Now the number of intervals that we want can change. It doesn't have to be the same every time. However, the recommended number of intervals is between 5 and 20. If it's less than 5, at that point, it's like, why are we even putting them into groups, into these intervals, when we don't really have many intervals to begin with? That would just make it ungrouped data. And then if you have more than 20, it's just like, holy crap, why do we have so many freaking intervals here? This is just kind of over the top. This is too much. So the recommended number is between 5 and 20. Chances are if you have less than 5 intervals to make it, you should just use ungrouped data. Again, we're dealing with intervals. What I'm discussing at this point is grouped data, meaning that the researcher themselves creates the groups that we're splitting these people into. So recommended number is between 5 and 20. I like round numbers, or I like intervals of 5. Personally, that's my personal preference. So I went with 10 because that's easy to divide, and it's just easy going. So again, to find the interval width, we take the real range, which we calculated before as 176, and divide it by 10. Again, this is the number of intervals that I have chosen. You can choose 5, you can choose 20 if you so please, but I went with 10. And that equals 17.6. So, okay, we have our interval width of 17.6, but actually not yet. So considering that all of our data were, none of our data in our original data set here, none of these numbers had decimals. They're all round, even numbers, or at least whole numbers, not even. I mean, we have a 17 here. That's odd. But none of our numbers have decimals. So when we make these interval widths, we want to make sure that those interval widths don't have decimals. If we did have decimals in our interval width in our original data set, it'd be fine to leave it at 17.6, but we don't. So in order to remedy that, in order to correct that, we must round up to the nearest degree of accuracy, which in this case just means numbers that match the original data set. So all our numbers were whole numbers in our original data set, no decimals. That's how we want our interval widths. You always round up. Now this is 17.6, so even when you round up, it would be 18. But even if we had an interval width of, let's say, 17.1, we would still be rounding up to 18. It's just if it crosses over the threshold of 17 at 17.1 or 17.2, we're just going to go all in and go straight to 18. So we have our interval width of 18. So now we have, for the first two steps of finding the real range and finding the interval width, now we move forward to constructing the frequency distribution. One important thing about the frequency distribution, at this point, we're creating the intervals. So just like in our age example that I mentioned earlier, I said, oh, 17 to 22, 23 to 28. I made it a point to count to make sure that the interval widths, so the length of the size of 17 to 22 is the same size or width as 23 to 28. It's important to do that because you have to have the same interval length for all of your intervals. You can't have 17 to 22 and then 23 to 50 and then 50 to 52. It just makes no sense. You want to keep them all the same exact size. So keeping in mind that the lowest number in our example in our data set was 0, we start at 0. That's simple. And then we have 18 as our interval width. So 0 counts as a data point. So 0 is 1, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, 9, all the way up to 17. So each interval width is 18 lengths long, or however you want to say it. So 0 to 17 is not actually a width of 17 because we count 0 as a number as part of the width. So it's 0, 1, and then we start counting 1, 2, 3, 4, all the way to 17, and that's 18. A width of 18. The same thing goes for 18 to 35, 36 to 53, all down the board. And again, you want to make enough intervals to where you cover all your data. So again, the lowest number, the lowest point in our data set was 0, and the highest was 176. Now our intervals here don't stop at 176, it actually stops at 179. That's fine because it covers all the data, the lowest to the highest, and we're keeping them all the same width. We don't want to have this last interval size or interval width be 162 to 176 because that would make them unequal sizes throughout for all the intervals. So intervals must have an upper and lower boundary, which just means the lower boundary is the low number of the interval and the upper boundary is the high number. So 0 is the lower boundary, 17 is the upper. 144 is the lower boundary, 161 is the upper. You get the idea. So again, they have to all have an equal width for each variable, or excuse me, for each interval. Doesn't matter if, it doesn't matter that we have it goes up to 179. We're not going to change it to 176. We're going to keep everything as is. Boom, that's the interval width. We're done. They never overlap. Keep in mind that we're doing frequency distributions. We're counting how many people are in each group, or how many in this particular instance, how many kids watch TV between 0 and 17 minutes a day? How many kids watch TV between 18 and 35 minutes a day, and all the way down the line? If we have overlapping intervals where we have 0 to 17 and then 17 to 35, or just, if we do stuff like that, then for a kid who's on that cusp, who's at 17 minutes a day, they're being counted twice. So they're in the 0 to 17 interval and also in the 17 to 35 interval. And we don't want to do that because it's going to just screw up our data. It's not going to be an accurate representation of what we have. So we make sure that our intervals never overlap when we're doing frequency distributions, because we're essentially counting how many people fall in each group. And again, these are rounded to the nearest degree, to the same degree of accuracy. So if you have whole numbers, you're going to round those interval widths from 17.6 to 18, like we did previously. So once we have all of these intervals, these are all the intervals from here. So 0 to 17, 18 to 35, etc. We can graph them, put them in, or not graph them, excuse me, put them in this table. And then once we have the intervals all lined up like that, then it's just as simple as, okay, how many kids watch TV from 0 to 17 minutes a day? And we go back to the original distribution of data here, back to the original data set and just count, okay, 7, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wait, I think I missed one. Well, anyway, I'm not going to get into it right now. But we have 0 to 17, we count 11 different people that fall into that interval. I probably missed one because I got to 10, but you get it. So you'll do that for all of the groups, all of the intervals that we, the researchers or the statisticians, have created. And that gives us, this is our simple frequency distribution. This is what I'm talking about. When we graph it, it's going to look differently. We're going to, make a graph, but a simple frequency distribution is this. This is the end product of what we're doing. It's just a table that contains our intervals and our frequencies, or f of x, which is just the frequency of, each of these intervals. So we have relative frequency and relative percent distributions. Essentially, what that's saying is for each of the intervals that we have, like the 0 to 17, what percentage or what frequency of the entire data set does the 0 to 17 fall? So to do that, we take the observed frequency and divide by the total frequency count, or do that same thing and multiply it by 100 for percentage. So we have this first one here, the relative frequency for the interval of 162 to 179, there's one person. So we take 1 divided by 50, and we have a relative frequency of 0.02 and the relative percent of 2%. And that's kind of comes back to what we started with this lecture, where I was having you guys convert the decimals to percentages and vice versa. That this is the first instance in where we're kind of dealing with that. So you can do that for all of these, as I already have, and you're going to get how this is laid out. Pretty simple. So frequency distributions for ungrouped data. So this is, again, for group data, the statistician or the person making the frequency distribution, they're the one that's creating these different groups. So I know it gets a little complicated when I say group data and ungrouped data when we're both kind of dealing with groups. However, keep in mind that, again, with group data, you are making the groups. And with ungrouped data, the groups are kind of already available to you. So when we use sometimes instances that we use ungrouped data is when the dependent variable, which we mentioned in our lecture the other day, but the measured variable that we're looking at, the recorded variable, is categorical, or when the number of different scores is small, to where, as I mentioned before when I was discussing grouped data, I said, oh, between 5 and 20 intervals. If it's any less, you should probably go with ungrouped data. This is what I mean. If the difference in the scores is small, to where making groups of intervals is just not going to make any sense. So here are some examples. Categorical variable frequency. So we'll get into categorical variables when I discuss measurement, but ultimately they are groups of groups that you either are in or you're not. So you're either a biology major or you're not a biology major. And again, I'll get into more detail about that next lecture. But we have biology. We count up all the biology students. Chemistry, count up all the chemistry students and all the way down the line. And this is how we have, this is a simple frequency distribution for ungrouped data, which is using, in this case, categorical variables. These groups were predetermined. We didn't create these groups of, oh, biology majors, chemistry majors. They were already there. The statistician just kind of worked with what they got. When you have the difference, number of different scores is small. So let's say the number of naps that kids take in a day, or what have you, number of naps taken in a day. The highest is 4. We don't have any person that's taking more than 4 naps in a day. So to create a if we were going to make intervals out of this or grouped data, what would our group sizes be? What would the interval widths be? I mean, the real range is 5, and divide by, if we're going to make 5 intervals, 5 divided by 5 is 1. At that point, it's just like, well, I mean, why even make intervals? Let's just line up the number of naps they've taken, count how many people have done that, and then boom. We don't need to make intervals of, oh, 0 to 0, 1 to 1. No, just keep it as is, man. So there you go. So histograms and bar graphs. They are different, but they look relatively similar. The big difference between the two of them is that with histograms, the bars are touching, whereas when we are graphing ungrouped data, like the previous 2 examples I just showed you guys with the majors or the number of naps, how there weren't really enough to justify making intervals. With those kinds of graphs, though ungrouped data would use bar graphs where the bars are distinct and not touching each other. Histograms, nah, they don't worry about cooties. They're just like, give me your cooties, I'll touch you, I don't care. So again, this is used to graph the frequency of ungrouped data. So I would suggest starting with the frequency distribution table, which is what we've already done when we're looking at the children's TV time. My nose is itchy like a crazy mo. Sorry. Okay, I have a hair up there or something. Anywho, so you can start with the frequency distribution table because it's organized, it's simple, easy to read, and you can just easily convert that into a graph. So the rules of histograms is that the vertical rectangle, so each bar that you see in a histogram represents each interval, and the height is relative to the frequency that it is. So on the x-axis or the horizontal axis, you will have the intervals laid out. So 0 to 17, 18 to 35, 36, all the intervals that we had, those are going to be on the x-axis, on the horizontal axis. On the y-axis or the vertical axis, we have the frequency. So how many kids watch 0 to 17 minutes a day? Oh, that was 11. How many kids watch 18 to 35 minutes a day? Oh, that was, so we just graph that. The base of each rectangle, the base of each of the bars in these histograms, start and end at the lower and upper boundaries of the interval, respectively. And each rectangle is touching the other. There is no space between them. The only time there will be a space in the only time there will be a space in a histogram is if a particular interval does not have any scores in it. So if the frequency for a particular interval is 0, that portion of the histogram will be skipped and we'll just get to the next interval. So here's an example. It's a little shoddy. I am not the greatest grapher. So this is my work. Isn't it pretty and gorgeous? No. So again, you see here on the bottom, these are the intervals, which I did a scale starting at 0 and I just went by 20. So 20, 40, 60, 80, all the way to 180. And I just did the intervals on the bottom. And then, as I said, the rectangles or the bars that you see in histograms, each one starts at the lower boundary. So the first one was 0 to 17. So it starts at the lower boundary, ends at 17 at the upper boundary, which is somewhere around there. It doesn't have to be exact in my opinion, at least for this case. And the height of it is representative of the number of people that fit in that frequency interval. So here we had from 0 to 17, there were 11 people. From 18 to 35, there were 12. So we have this second bar at 12. 8 was in 36 to 53, so that's at 8, and so on and so forth. So again, the x-axis, the horizontal axis, contains the intervals, and the y-axis is the frequency. Oftentimes, a lot of students get those confused. They'll have the frequency as the x-axis, the horizontal, and the intervals as the y. That is incorrect. This is how it should be. Maybe your histograms will be prettier than mine. I hope so, because this is kind of woof. But this is the essential layout. Here's my simple frequency distribution table over here, just a straight shot of, okay, 0 to 17, there's 11 people. 18 to 35, there's 12. So that's displayed on the left here just to make it easy, because when I graph it, all I have to do is just look over, okay, there's 11, boom, and then it's just simple to do from there. So notice how all these bars are touching except in this interval here, because in the 144 to 161 interval, there were no students who or no children that watch TV between 141 and 161 minutes in a day. So instead of just having this bar touching that one and making it seem like there was someone there, we just skip it. So like I said, the only time when histogram bars do not touch is that if there is just no one to fill this interval. So we didn't have anyone between the 144 and 161 group. So when we graph it in our histogram, we just skip straight to 161 and graph the one person there. So bar charts, as I mentioned, these are used for ungrouped data. So for that example we had with the majors at Fresno State, the crim majors, chemistry, psychology, kinesiology majors, oh, that is always a hard one for me to say. But for those majors, that would be ungrouped data, or for the number of naps, recall that example where it was 0, 1, 2, 3, 4. We would use bar charts to graph these. These are similar to histograms in almost every sense, except the bars don't touch. So they're separate from one another. We're not going to have the biology majors bumping uglies with the chemistry majors. Their bars are separate, just like we see here. So since each group is clearly distinguished, and they're not kind of falling on the same spectrum of 0 to 17, 18 to 35. They're not all in the same range of numbers. There's not really numbers that we're dealing with, at least in this one. So we have biology, and we have it right there. We have chemistry in its separate bar, criminology in its separate bar, kinesiology in its separate bar, psychology in its separate bar. So bar graphs are used again for ungrouped data where we either don't have enough of differences of not enough different scores to justify making group data, making intervals, or the groups that we have are categorical, and thus the groups have kind of already been made for us, like biology, chemistry, criminology, kinesiology, and psychology majors. So that is graphing frequency distributions and kind of getting a little taste of more descriptive statistics in psychology, or just in statistics as well, and just kind of seeing how we work with that, how we what it looks like, you know, going from the ugly Excel sheet to, oh, here's the means for this whole thing, and then graphing that as well. So putting that in either a distribution table or graphing it using a histogram or a bar graph, depending on what our data is. So that is all I have for this lecture. So be sure to, you know, if you've been watching, hello, thank you. Nice to meet, nice to see you again, or rather nice for you to see me again. I guess I'm not watching you. Anyway, keep in mind that you have a quiz that is due at the end of this week. So make sure you just take care of that. And I will see you guys next time. So like and subscribe.